have essentially a free particle, except that in this case we're going to change the potential energy from x equals 0 to x equals L. Okay, so there's a region where the potential energy jumps, so it's not going to be equal to V equals 0. It will be some finite number, V naught, okay, between x equals 0 and x equals L. All right, and we're going to be looking at the solution to the Schrodinger equation for this problem. Okay, now to solve the Schrodinger equation for this, it's best to divide this problem into three parts, basically three regions. So you have for x less than 0, we call that region 1. Region 2 would be between x equals 0 and x equals L. And then we solve for psi for region 3 for x greater than L. Okay? So we solve for psi, the Schrodinger equation separately for each of those regions. And what we said that if E happens to be less than V naught, okay, so here's your V naught right here, and this is your E. So E is less than V naught, then the solution would look something like this. So psi on the left side, this is your region 1, okay, would be equal to E to the ik1x plus B times e to the negative ik1x, where a and b here are constants, integration constants. And this is basically the free particle differential equation that we had before. What was a k1 for this? Square root of k1 is square root of 2 times the mass times the energy divided by h bar. All right? And we said that in the middle of the box, psi, so this is region 2, psi would be equal to some constant c times e to the k2x plus another constant d times e to the negative k2x. And we said that k2 in this case is square root of 2 times the mass times v naught minus e over h bar. Okay? Note that this thing has an I in it. Okay? That means your psi there is oscillatory, it oscillates. But here, your psi, the exponential term does not have an I. There's no I there. Okay? And then on the right side of the box, or to the right of the barrier, you can say, this is what we call your potential barrier right here. To the right side of the barrier, region 3, you have a constant times e to the I k3x plus another constant f times e to the negative I k3x, where k3 in this case will just be the same thing as k1. Right? Now, why is there an I there in region 1 and region 3, but there's no I in region 2? So let's just do a quick review of how we solve the Schrodinger equation for a free particle. Remember h psi, let's just do psi 1, okay? Let's do h psi 1 equals e psi 1. That's your Schrodinger equation for the left side of to the left of your barrier, right? What's the Hamiltonian? What's the Hamiltonian for a free particle? Negative. Its kinetic energy operator is what? Negative h bar squared over 2m, second derivative of psi with respect to x. Okay, and our potential energy for the left side, region 1, potential energy here is 0, remember? And for the right side, that's also 0. So potential energy operator is 0. So 0 times psi, right? Equals E psi. Right? And if we rearrange this, we can write this as second derivative of psi with respect to x equals, I can move my constants to the right side. I'm going to get negative 2m e over h bar squared psi. Right? all I did was I did some rearranging here. This term right here will just drop out. And I can move everything to the left side. So I have second derivative with respect to psi plus 2me over h bar squared psi is equal to 0. So quick review, if you have this type of differential equation, remember if you have something like ay double prime plus by prime plus cy equal to 0, what's the solution to these types of differential equations? Your psi here is going to be what? Your y here is going to be e to the sx, where s depends on what a, b, and c are, right? So what would our psi be in this case? Psi would be, let's call it e to the sx. A specific solution to this equation, to this differential equation. What's the second derivative of e to the sx? Se to the sx would be the first derivative. Second derivative would be s squared e to the sx. So plus 2 times the mass times energy over h bar squared, and psi is just e to the sx. That's equal to 0. So you can factor out e to the sx. So you have s squared plus 2 times the mass times energy over h bar squared equal to 0, which means that e to the sx is going to be a solution provided s is equal to 1. Provided this term is equal to 0, right? Because the function itself cannot be 0. So you have to have s squared plus 2me over h bar squared must be equal to 0. That means what are the allowed values of s then? Okay. Let's rearrange that. So s squared is negative 2me over h bar squared. And you'll notice this whole expression is positive, right? So if you want the square root of this term on the right, you're going to be taking the square root of a negative number. So it's just negative 1 times that. So s will be equal to I times the square root of 2me divided by h bar. So plus or minus, right? So 2 possible values for s. And that's why we said our psi is a linear combination of e to the I, and this is what we call our k1, remember? So it's I k1x plus c2 e to the negative I k1x. So it's plus or minus ik, k1 is are the allowed values for x. So that's for region 1. And that's what we had before up here, except that we used capitals A and B, letter A and B for our constants. All right? Now for the middle of the box, there isn't going to be an I. And the reason for that, once you get to the middle of the box, you basically have the same differential equation, except that when you get to this point right here, what are you going to have? Instead of 2m, okay, when you get to this point down here for region 2, all right? Let me see. For region 2, you're going to have s squared equals, instead of that, you're going to have negative 2m v naught minus, let's see, e minus v naught, okay? You're going to get 2m, hold up. When you get to this point over here, you will say that s squared is equal to negative 2m e minus v naught over h bar squared. Because if you go back here, this is going to have a v naught term over here. Okay, so when you move that v naught over to the right side, you have an e minus v naught. So instead of e, you're going to have e minus v naught. All right? So when you do that, So instead, if you have that instead, what happens now is you're going to say that S would be what? Oops. What's E minus V naught? We're looking at a situation where E is less than V naught. So what's E minus V naught? Positive or negative? This E naught is going to be negative. So negative of a negative number is going to be a positive number. So when you take the square root of this, there isn't going to be an I. Actually, if I can rewrite this as, instead of saying minus 2m E minus V naught, what I'm going to do is I'm going to say that's 2m times V naught minus E. Right? Negative of x minus y is just the same thing as y minus x, right? Flip the two. So it's going to be 2m V naught minus E over h bar squared. That's going to be my s squared. So when I take the square root, I'm not going to come up with an I in the expression for psi. So this is just going to be square root of 2m V naught minus E over h bar squared. Or if you take the h bar squared out of your square root sign, you'll have square root of 2 V naught minus E over h bar. And this is what we call K2. Okay? Plus or minus. Okay? So it's plus or minus K2. All right, and then this same problem for the right side is the same as for the left. So you have an I there. And K3 you'll see is just the same as K1. All right, so that's your the three parts of your side, depending on what the location is. And like we said before, you're going to have 6 unknowns, A, B, C, D, E, and F, right? So in order for you to determine what those unknown constants are, you have to have 6 equations. And the requirement that psi must be continuous and its derivative must be continuous will give you 4 equations. Because at x equals 0, okay, what we're really saying is this: psi at x equals 0, psi 1 must be equal to psi 2. That's the continuity condition, right? So what is psi 1? A, E, I, K1 times 0, right? Plus B, E to the negative I, K1 times 0. That's your psi 1. That must be equal to psi 2. What is psi 2? C, E to the K2 times 0 plus D, E to the negative K2 times 0. So what is E to the 0? That's just 1, that's just 1, that's just 1, and that's just 1. So we have to restrict A plus B must be equal to C plus D. Okay, so that's one of the equations that you can use to determine what those constants are. So what would you do if you want the first derivative to be continuous at x equals 0? So here, this is the condition that must be satisfied when we say psi is continuous. I shouldn't be making that uppercase, huh? Never mind. Psi 1 equals psi 2. So continuous, psi is continuous there. What would be the requirement for the first derivative? First derivative of psi at x equals 0 must be the same whether you're coming from the left or you're coming from the right. So psi 1, the derivative of psi 1 must be equal to the derivative of psi 2 at x equals 0. So what's the condition here? What's the first derivative of psi 1? A, and you have e to the I k1 x. What's the derivative of that with respect to x? multiply that by ik1, okay, plus b negative ik1 e to the negative ik1x. So that's the derivative, first derivative of psi at x equals 0. That must be equal to its first derivative of psi 2, which is c e to the k2x, so multiply this by k2, plus d e to the negative k2x, so you multiply this by negative k2. All right. So, and what's our x here? Our x is 0, so this is 0, that's 0, that's 0, and that's 0. So that's just going to be 1, that's just going to be 1, that's just going to be 1, that's just going to be 1. So our second boundary condition, continuity at x of the first derivative would say that ik1a minus ik1b must be equal to k2c minus k2b. Okay, so you can do the same for the right side. For the right side, you're going to have to plug in x equals L. Right? So if you want continuity at x equals L, what do we say? At x equals L, psi psi 2 must be equal to psi 3. Okay? Because at x equals, remember, you have psi 1 here, psi 2 over here, and psi 3 over here. So it must, at x equals L, your psi 2 and psi 3 must meet. So what is psi 2 at x equals L? C e to the k2L plus d e to the negative k2L must be equal to e times e to the I k3L, but k3 and k1 are the same, so let's just call that k1L plus f e to the negative I k1L. Right? So for your homework, do the fourth one, which would be continuity of the first derivative at x equals L. All right. So anyway, with those 4 equations, you still need 2 more, right? Because you have 6 equations. You need 6. You have 6 unknowns. So you need 6 equations, 6 unknowns. So we have so far have 4 equations in 6 unknowns. We can eliminate 1 more unknown if we just take the situation where all the particles, okay, that happen to be to the right of the barrier would be moving away from that barrier. So we're going to insist that piece of x, the momentum is going to be h bar k3 or positive h bar k1, right, on the right side of the barrier. Basically what this means is this. If you go back to your expression for psi 3, what did we say psi 3 was? To the right of the barrier, psi sub 3 is what did we say was e times e to the I k1x plus f e to the negative I k1x. If you remember, this thing right here is an eigenfunction of the momentum operator, right? This corresponds to a stationary state with px equals h bar k, right? And this is an eigenfunction of the momentum operator, which corresponds to a momentum of negative h bar k. So we're only going to look at situations, okay? We're only interested in situations, cases where the particles on the right side of the barrier are moving away from that barrier to the right. So what would that mean? We're going to eliminate this f this term right here. We're going to say f is equal to 0. So that gives us 5 unknowns. All right? So what we can do then at this point is, okay, we got 4 equations, 5 unknowns, right? We can take the ratio of 2 of the unknowns, right? And that ratio, the ratio of the square of that ratio is called the transmission probability. That would give us enough information to figure out what's called a transmission probability. And you'd be able to solve for it using algebraic manipulation. You can find that the transmission probability is equal to 1 plus this expression right here, e to the k2l minus e to the negative k2l. The whole thing is squared, divided by 16 epsilon minus 1 minus epsilon, and then you have to take the reciprocal of that expression. Okay, so that's kind of a lengthy algebraic derivation. You should be able to Google that. There's like 3 or 4 websites that show that derivation to you, so you can look it up. All right. Now this epsilon, it's probably not going to give you this actual expression right here. This is the one from your textbook. Just be aware of the definitions here. Epsilon is defined as E over V naught. Okay. So remember that means how your energy, the actual energy of your particle compares to the barrier. So if epsilon is less than 1, then you're saying that E is less than V naught, right? If epsilon is less than 1. All right, and this expression can also be simplified if K2L, okay, this K2L right here, that's K2L right here, that happens to be significantly larger than 1, much, much larger than 1, you can reduce that expression to this expression right here, which is a little simpler. Basically, what does this expression tell you? For the same epsilon, okay, for the same ratio of energy to the barrier, the potential barrier, the transmission probability is proportional to e to the minus k2l. So, in other words, your transmission probability is directly proportional to e to the minus k2l. What does that mean? The larger the L, what does that mean? This expression right here is an exponential decay. A bigger L value means e to the negative, e to a big negative number would be small. So in other words, the wider your barrier is, the larger that L is, the less likelihood that your particle is going to transmit through the barrier, be able to traverse the barrier. Okay? Let's take a look at to the right, yeah. Mm-hmm. Not really, because what we're really interested here is we're really more we're focusing on just transmission through the barrier. Okay, and yeah, if you look at your expression right here, you'll notice the amplitude of this, the value of these coefficients right here. We say it's a transmission probability because if you look at your E here, that's a coefficient, okay, for the eigenfunction with a momentum of h bar k, right? Positive h bar k, moving to the right while being in the third region, to the right of the barrier. A, on the other hand, would be the amplitude of the wave approaching the barrier. So this is what you would call the amplitude a squared, actually. Remember, our probabilities would be proportional to the square of the coefficients. So this A gives you the amplitude of the wave approaching the barrier from the left. This B right here, look at this B. This is the coefficient for e to the negative ikx. This corresponds to a momentum of negative h bar k left of the barrier. All right? So B, absolute value of B squared, would be the probability that your particles would be reflected back. So what we're trying to do here is we're comparing what's the likelihood that if you have particles moving towards your barrier, okay, what's the likelihood that it's going to traverse the barrier as opposed to it's being reflected back. Okay, so E squared over A squared. Okay, so E squared over A squared will give you the probability of particles being transmitted. B squared over A squared will give you the probability of particles being reflected. Okay, reflected back, bounced off the barrier. So basically what you'll find is if you plot your transmission probability versus epsilon, you'll find that what happens as epsilon increases. As the actual energy approaches 1, approaches the barrier energy, so as epsilon approaches 1, what happens? The transmission probability increases. So the closer the energy is of your particle to the barrier potential, the more likely it's going to be able to traverse that potential, traverse that barrier. Now, these plots right here are labeled with a value for this expression right here, okay, which your book does not give a name, but that's basically 2m v square root of 2m v naught over h bar times L. This, okay, so each of these curves represent a value for this expression right here. So this tells us how, this will tell us how the transmission probability depends on the mass, m, and how it depends on the L. Okay? So a larger value for this, for example, 10 right here. Okay? This is the curve for 10, and this is for 4, and that's for 2. So this expression right here is larger for down here, for the curve down here. Let's label with a 10. All right, what does this mean? The larger the L, the wider your barrier. What happens when your barrier is wider? What happens to this expression? This becomes larger, right? So this would have, down here would be a wider barrier. That's a larger L for the same M. So if you're looking at the same mass, down here you'll have a wider barrier. So what happened? What did we say the transmission probability is? The wider the barrier, the less likely the particle can penetrate the barrier, can traverse the barrier. Okay? Now, what about the effect of mass? Let's say we're comparing different particles, okay, everything the same except for the mass. Same barrier, different masses. What happens? Again, so down here again, the higher the mass, so this would correspond to a larger mass for the same barrier width. Okay, the same, for all factors being the same, a larger mass would be less likely to tunnel through the barrier. Okay?